Okay, we're going to look into something called hypothesis testing now. So the title of this lesson, even though I don't have, is going to be hypothesis testing or significance testing. We'll be playing with this quite a bit. So we're going to start off looking at a problem. Okay, so vehicle accidents can result in serious injuries. You can read this obviously. And so this has to do with the fact of a EMT response team, emergency medical team response. So several cities have begun motor paramedic response times to monitor paramedic response times. One city, the mean response time is mu equals 6.7. So that is the true mean, okay, at least for 1 year, for the previous year. And that previous year had a standard deviation of 2, right, 2 minutes. So 6.7 on average, give or take 2 minutes. The city manager shares this information with emergency personnel and encourages them to, quote, do better next year. At the end of the following year, the city manager selects a simple random sample of 400 calls involving life-threatening injuries and examines the response times. For this sample, the response time was 6.48. Do these data provide good evidence that the response times have decreased since last year? Okay, so let's look at the hypothesis. Okay, the hypothesis, there are two competing hypotheses. Okay, the first hypothesis is that response times are the same. And the second one is response times have gone down. Okay, sorry this is hard to read. What that means is what we're talking about is it's a referendum on the actual mean. Is the mean still 6.7 or is the mean now less than it was last year, 6.7? So those are our two options. Now, let's take a look at the evidence we have. All right. Last year, the mean was 6.7, and the standard deviation was 2. And that was a sigma. Now we know this year, with a sample of 400, we have an average, a sample mean of 6.48. Now, this is not a population. This is not the second year's population average, right? It's not the true average, but it is less than the population mean from the previous year. So the question is, how likely is the evidence? And here's what we have to do in order to evaluate this problem. We have to ask the question, if mu is 6.7, so suppose that the mean is still 6.7, how likely is an x bar of less than or equal to 6.48? Okay, that's what we're trying to figure out. If we take the 6.7 as the true mean, how likely is a response time amongst 400 responses of 6.48? Okay, well, here's how we're going to do this. First of all, we have a sample size of 400, and we're talking about a sample mean of 6.48. We also know that the original distribution had a mean of 6.7 and a standard deviation of 2, so we're going to look again at a sampling distribution of the sample mean. Now, we know here that we have a simple random sample, okay? That means we have independence, and we also know that n is bigger than or equal to 30, so the sampling distribution of x bar is normal with a mean of 6.7, the same as the original mean, and a standard deviation of 2, which is sigma, divided by a square root of 400. Okay. So what we'd like to know is what are the chances that x bar would come in at 6.48 or less if indeed the mean were actually 6.7 and the standard deviation were actually 2. Okay. Well, we can go ahead and compute that. we have a standard deviation here, and I'll go ahead and pull up the calculator. We have a standard deviation of 2 divided by the square root of 400. So a standard deviation of 0.1, that came out nicely. And we know the mean is 6.7. So if we want to find this, we're going to create a z-score. Okay, so z is going to be equal to, first of all, we want to do that over here, x bar, the number of interest, this number of interest, minus the mean of the sampling distribution, divided by the standard deviation of the sampling distribution. So z is better be less than or equal to, we're going to have 6.48 minus 6.7 divided by 0.1. So we get a z-score of negative 2.2. Now we know this is a normal curve, so we can go ahead and use normal CDF to find out the probability that this happens. So we're going from negative infinity to negative 2.2. And this says z-score, so the standard deviation is 0, or the mean is 0 and the standard deviation is 1. So the chance of this happening is 0.013. So if we assume that the mean, the average response time is still 6.7 from last year, okay, that we assume that's the same, and the standard deviation is still 2 from last year, and that's a reasonable assumption. If we have to assume something, it's not something bad to assume. If we assume those things are still the same as from last year, then the chance that we would go out and get 400 calls randomly sampled and find out that the average was 6.48 or less is only 1.3%. So if the original claim is true, the chance that what we saw happen is very, very, very small. Only 1.3% of the time that's going to happen. So we have a choice to make. Do we stick with what we know? Stick with last year's numbers that were solid numbers? Okay. Do we stick with those numbers, or do we take our chances and say, I think that the number has gone down? Okay. If we do that, there's always a chance of error, and the chance of error is 0.013. Okay. Let's formalize this now. This idea of using sample data and comparing that sample data to population data to find out how different they really are. This idea is called hypothesis testing, and the first thing we need to be able to do is write down what the hypotheses are. Now, it's a great word, right? The null hypothesis. The null and alternative hypotheses. The null hypothesis is the claim that's being tested against. Okay, so the null hypothesis is the status quo. Okay, so for instance, we didn't know any better, so we had to use the number we had from last year with the ambulances. Okay, the status quo is the thing that we assume is true until you can show otherwise. The alternative hypothesis is the claim you're trying to make. Typically, what you're trying to show is true. Right? We're trying to buck the trend. You wouldn't go ahead and do a test unless you're trying to show something new. Okay, so the notation is this. For the null hypothesis, we write capital H with a subscript 0, colon, and then for when we're talking about means, we say the mean is equal to some number. Okay. The alternative hypotheses in the previous, so in this case actually, we can write it as the previous. The null hypothesis was the mean is 6.7, same as last year. Nothing has changed. That's the null hypothesis. The alternative hypothesis for us was the mean is now less than 6.7. That's what we were trying to show is true. So really, there are three different options for alternative hypotheses. We could try to show, as we did, that the mean is less than 6.7. We could have tried to show that the mean is greater than 6.7. That would have been an alternative to being equal to 6.7. And another alternative to being equal to 6.7 is just not being equal to 6.7. So no direction, basically. Okay? So we can either show that it's less than 6.7, greater than 6.7, or not equal to 6.7. With these hypotheses, the same number will be here as here every single time. The only thing that will differ is the sign. Is it equals to or some other thing? All right. So here's the mechanics that we actually did in that problem. We call this the test statistic, and it really is just a z-score, but it's got a special name and a special reason for doing this. In our case, we had z, and our estimate was x bar, our hypothesized value was mu, and our standard deviation of the statistic was sigma over the square root of it. Now, this doesn't always have to be the same, okay? But for our case, we used a z, and that's what we got. So, then we have this idea of something called a p-value. Okay, so our test statistic was z equals negative 2.2. Then we have a p-value. So this is the probability, assuming that the null hypothesis is true, that we see what we saw, right? That the observed outcome would take a value as extreme or more extreme than that was actually observed. We call it the p-value. So in our case, our p-value in that previous problem was 0.013. Now, this is a very small p-value. The smaller the p-value, the stronger the evidence against H0. What we're saying here is that if we say we're going to reject the null hypothesis, then the chance that we do that in error is 1.3%. Okay? So the smaller the p-value, the less chance of error you have if you decide to reject the null hypothesis. Okay, the last concept here that we want to talk about right now is called statistical significance. And the idea here is that sometimes somebody says, I want you to do this test, but I only want you to give me positive results if your p-value is very small. And the significance level is simply, that's alpha, right? It's not an A, it's an alpha. The significance level is just some level somebody says, you know what, I'm willing to accept a 5% error. That would be an alpha of 0.05. I'm willing to accept a 1% chance of error. This value that we got here, p-value of 0.013, is significant at the 0.05 level. It is less than 5%, but it is not significant at the 0.01 level. Okay, it is bigger than 1%. We might think about these if you're in some kind of industry, maybe healthcare of some kind, and you're trying to test some kind of drug. You want to make sure the drug actually does what it's supposed to do. Your p-value in that case has got to be very, very small because you don't want to make a mistake. Okay. In the case of electoral politics, there's a lot more wiggle room. If you make a mistake in electoral politics, the worst thing that happens is somebody loses an election. Nobody dies. Okay, so in that case, if you're trying to prove something about politics, you might be fine with a 0.05 significance level. But with medicine, you're probably going to want something smaller. Okay. Okay, so let's look at one more problem, and then we'll break this down next time. So the Cobra Cheese Company buys milk. Again, we have this excess water can be detected. So sometimes you're going to add water to milk to water it down so you get more bang for your buck. And so what's happening here is we want to find out, did the suppliers water down the milk that the Cobra Company bought? So we can detect it by freezing the milk. The freezing temperature of natural milk varies normally, with a mean of negative 0.545 Celsius and a standard deviation of 0.008. That's true, right? Those are true values. If we add water, okay, then it raises the temperature towards 0 when you freeze it, okay? So Cobra's lab manager measures the temperature of the random sample of 5 containers of milk from one producer. The mean is negative 0.538. The question is there any evidence here that the milk has been watered down? So let's look at what we have here. Our null hypothesis is going to be that the milk is not watered down. Indeed, it freezes at negative 0.545. The alternative is that the milk has been watered down, and therefore the freezing point is significantly larger than negative 0.545. Those are our two options. Those are hypotheses. Okay. Now we look at the evidence we have. Now we do our test statistic. We're trying to figure out Z. So first of all, let's take a look at something. They tell us something very interesting here. They tell us that varies normally, typically. So that milk varies normally, the freezing temperature of the milk varies normally. That means that the original distribution was normal. Okay? And remember, we need that if we're doing sampling distributions. We need to know the original distribution is normal or our sample size is large. Well, the manager here took a mean measurement of negative 0.538 out of 5 containers. Now this isn't a large sample, but since the original distribution is normal, we're good to go. Okay, so that means that the sampling distribution is normal too. Remember, we also know from the get-go that sigma was 0.008. So our test statistic is going to be z equals the estimate minus the claimed mean divided by the standard deviation. So we're going to have negative 0.538 minus negative 0.545. And we have sigma, which is 0.008 divided by the square root of 5. Now, before we go any further here, I just want to make a point that the sample mean is larger, closer to 0, than the population mean. What we're trying to show here is it large enough so that we would not be able to attribute that to chance alone. Okay, so we're trying to say, is it large enough so that chance is not going to play a factor here? What do we get for a z-score? Put it in the calculator. Negative 0.538 plus 0.545 divided by 0.008 over the square root of 5. Oh, doesn't matter there. 1.956. That's nearly 2 standard deviations from the mean. Okay, so our test statistic is 1.956. That's giving me a sense that possibly this might work. Remember, the curve is normally distributed. We have a z-score, so we can go ahead and use normal CDF to figure out our p-value. Now we're looking for the chance that the value is this or bigger. So we want to find out the chance that our z-score is 1.956 or bigger. So we go back to the calculator. And we go from 1.956 to infinity. Leave everything else the same. And we get 0.025. That's our p-value. Now, the question is this good evidence that the producer is adding water to the milk? Provide appropriate statistical evidence to justify your answer. Now, what we're saying is that there are two options. Either the milk is not being added water to, water's not being added to the milk, or water is being added to the milk. So the producer has two, or the Cobra has two options. They can either not rock the boat and not accuse their suppliers of watering down milk. That's option one. Or they can reject the null hypothesis and say, you guys are watering down the milk. If they do that, however, and they screw up, there's a big problem, right? If it turns out that they launch this big investigation and their suppliers are doing nothing wrong, they're going to lose all their business. So they have to be very, very careful. And the question is, how much error are they willing to risk? Okay, what we're saying is, if they say that, if they accuse their suppliers of watering down their milk, they're willing to accept a 2.5% chance of being wrong. Okay, that's what the p-value means. If we reject the null hypothesis and favor the alternative, we have a 2.5% chance of doing that in error. Okay, all right, so I know this is a lot now. We're going to be spending a lot of time on this. This is the last big topic in AP Statistics. Thanks, guys.